Lesson: Supervised Learning for Predictive Data Mining. Supervised learning is a cornerstone of predictive data mining within AI-enhanced data mining techniques. It involves training a model on a labeled dataset where the outcome variable is known to make predictions or decisions without human intervention. This method is particularly useful for tasks such as classification and regression, where the goal is to learn from past data to predict future outcomes. The practical application of supervised learning in the field of predictive data mining is vast, spanning industries such as finance, healthcare, marketing, and beyond. At the heart of supervised learning is the concept of a model, which can be thought of as a mathematical function that maps input data to an output or label. The process begins with the collection and preparation of a dataset, which includes both input features and corresponding output labels. For example, in the context of predicting customer churn, the input features might include customer demographics, purchase history, and engagement metrics, while the output label would be whether the customer churned or not. The dataset is then divided into a training set and a test set, allowing the model to learn from one subset and be evaluated on another. Pause training, sir. One of the most widely used tools for implementing supervised learning is Python, with libraries such as scikit-learn and TensorFlow providing robust frameworks for building predictive models. Scikit-learn, for instance, offers a vast array of algorithms for both classification and regression tasks, including decision trees, support vector machines, and k-nearest neighbors. These tools are designed to handle the entire machine learning pipeline, from pre-processing and feature selection to model training and evaluation. For example, a data scientist might use scikit-learn to pre-process data by normalizing features and handling missing values, then apply a random forest classifier to predict outcomes. The choice of algorithm in supervised learning often depends on the specific characteristics of the problem at hand. For instance, decision trees are intuitive and easy to interpret, making them suitable for scenarios where model transparency is crucial. However, they can be prone to overfitting, particularly when the tree is very deep. In contrast, ensemble methods like random forests or gradient boosting combine multiple decision trees to improve accuracy and robustness. These methods have been shown to perform well on a wide range of datasets, as they reduce the variance of predictions by averaging over many individual models. Another critical aspect of supervised learning is the evaluation of model performance. Common metrics for classification tasks include accuracy, precision, recall, and F1 score, each providing different insights into how well the model is performing. For regression tasks, metrics such as mean squared error and R-squared are often used. It is essential to choose the right metric based on the business context and the specific goals of the prediction task. For example, in a medical diagnosis scenario, precision might be more important than accuracy to minimize false positives. Real-world challenges in supervised learning often revolve around data quality and quantity. High-quality data is critical for building effective models, yet many organizations struggle with issues such as missing data, imbalanced classes, and noisy inputs. Techniques such as data augmentation, resampling, and feature engineering are vital to address these challenges. Data augmentation involves generating new data points by perturbing existing ones, which can help mitigate the problem of small datasets. Resampling techniques, such as oversampling the minority class or undersampling the majority class, can help address class imbalance. Feature engineering, on the other hand, involves creating new input features from existing ones to improve model performance and interpretability. A compelling case study illustrating the power of supervised learning in predictive data mining is its application in credit scoring. Banks and financial institutions use supervised learning models to assess the creditworthiness of loan applicants. By training models on historical data, which includes both applicant characteristics and loan outcomes, these institutions can predict the likelihood of default for new applicants. This not only aids in making informed lending decisions, but also helps manage risk and reduce potential losses. A well-known example is the use of logistic regression and decision tree models in credit scoring, which have been shown to outperform traditional statistical methods. Moreover, the integration of AI-enhanced data mining techniques in predictive analytics has been facilitated by the emergence of AutoML systems. These systems automate the end-to-end process of applying machine learning to real-world problems, making it accessible to professionals without deep expertise in the field. AutoML tools, such as Google's AutoML or H2O.ai, automatically select the best algorithm, tune hyperparameters, and perform model evaluation, significantly reducing the time and effort required to develop predictive models. These tools have demonstrated their ability to produce models that are competitive with those developed by human experts, thereby democratizing access to advanced analytics. The practical implementation of supervised learning also requires considerations of scalability and deployment. In many cases, models need to be deployed in production environments where they can process real-time data and provide predictions without delay. This necessitates the use of scalable infrastructure and efficient algorithms that can handle large volumes of data. Cloud platforms, such as AWS, Google Cloud, and Azure, offer scalable services and infrastructure for deploying machine learning models, allowing organizations to integrate predictive analytics into their operations seamlessly. In conclusion, supervised learning is a powerful tool for predictive data mining, offering actionable insights that can drive decision-making across various domains. By leveraging practical tools and frameworks such as scikit-learn, TensorFlow, and AutoML systems, professionals can build robust models that address real-world challenges. The effectiveness of these tools and techniques is underscored by their widespread application in industries such as finance, healthcare, and marketing, where they enable organizations to leverage data for strategic advantage. As the field continues to evolve, the integration of AI-enhanced data mining techniques will further enhance the ability of professionals to derive value from data, ultimately leading to more informed and impactful decision-making.